So as you watch this video, make sure that you are filling in your notes packet as you go. Okay, so for starters, we're going to look at two different forms of our function. We can look at our function in the form after the long division, which is what we have here, where we've got something plus a fraction. And remember that something is the quotient from your long division. And so the quotient from the long division, remember, in terms of what we're finding when we're analyzing our rational functions, that quotient tells us about our non-vertical asymptote. So for the first example, our non-vertical asymptote is y equals 5. And in the second one, non-vertical asymptote, y equals 2x minus 3. Okay, well, so then if we take a look at the rest of what we're given in these functions, we've got this fraction, right? So we've got a numerator and a denominator. Well, when we go to write these fractions, remember that you're writing the quotient, the non-vertical asymptote, plus the remainder, which is what I've just highlighted in green here on the top. Here's the remainder, over the original denominator. Well, remember, the original denominator told us about the vertical asymptotes. Those are our non-removable discontinuities, right? They're the fixed discontinuities. And so they still tell us the same thing. If this is the original denominator, we still know about our vertical asymptotes. So for the first example, we've got one at x equals -3 and x equals +1. And for our second example here, we've got a double asymptote. Just means that the sign chart's the same on either side. Doesn't mean write it twice. We've got that at x equals +2 and another asymptote, vertical asymptote at x equals -8. Okay, so then the rest of what we know is this numerator. That numerator, remember, is the remainder. And if you think about what we're doing when we're using the remainder, we use the remainder to determine where we're intersecting with the non-vertical asymptote. So in this case, we are going to intersect, in the first one, our non-vertical asymptote at an x value of +2. In the second example, we're intersecting our non-vertical asymptote at an x value of -1. But then for both of these, we need to determine the y value as well. So in this first one, our y value is going to be when we're crossing the non-vertical asymptote, but we're crossing at a y value of 5. So we don't have to calculate anything. It's just going to be 2, 5. The second one, we're looking for what's happening when we're crossing the non-vertical asymptote. In this case, the non-vertical asymptote is this oblique line. So what we need to do is we need to substitute -1 in here for x. So we'll plug it in. 2 times -1, -2. -2 minus 3 is -5. So we can still determine our intersection point. So that tells us if we have our equation in this form after the long division, that what we know about our function is we know about the non-vertical asymptote, and we know about the vertical asymptotes, and we know about the intersection with the non-vertical asymptote. Okay, so again, you are filling in your notes as we go, so there's a spot for the conclusion right there. Okay, so this was the form after the long division. Well, we could also be given equations in the original but factored form. And we can find everything possible from this form. We've done that a gazillion times. However, what we know right away, without having to do all the long division, we can identify the vertical asymptotes, the zeros, the wholes, right? We can do that relatively quickly by now, I hope. And so go ahead and on each of the 3 of these, find that information. So as you can see from the denominator, we're identifying our vertical asymptotes. In this last example, we've got a removable discontinuity or a hole, so we took that out. The numerator tells us about our zeros, aside from the hole. And the only one that canceled at all was this last one, so that's the only one with a hole, and it happens at an x value of -1. To find the y value, remember you're plugging that x value in, but only to what's left. So excluding this x plus 1 fraction, because that's going to give us an undefined value. We don't need to know that, we already do. So then from there, what we can do is we can identify what type of NVA we're going to have before we even find it. So for that, let's imagine that we are going to do the long division. We're going to look at the degree of the numerator versus the degree of the denominator. So in this first example, the degree of the numerator, if we multiplied all of this out, which we're not going to do, is we'd have an x squared here times an x times another x. We'd have an x to the 4th power in the numerator and a plain old x in the denominator. So if we went to do the long division, we'd be looking at this. Okay, well, x goes into x to the 4th, x cubed times. So what that tells us is we've got a non-vertical asymptote that has a cubic function. Well, cubic is going to be non-linear. Okay, so we can do kind of the same thing for the other two. If you look at the degree of the numerator in the second one, the numerator's degree is x, where the denominator's degree, if you multiplied that out, you'd have an x squared. All right. Well, if we went to do the long division here, we're looking at how many times does x squared go into x? Well, without fractional powers, we can't do it. So it goes in 0 times. So what that tells us is we're going to have a horizontal asymptote. And more specific than that, it's going to be the x-axis as our non-vertical asymptote. And in our last one, again, it doesn't actually impact it here, but we're just looking at what's left over after we cancel. And so the degree of the numerator, x squared, the degree of the denominator, also x squared. So in this case, the degree equals. And when you do that for your long division, you just end up with 1 in this case, and it all depends on the coefficients, but in this case, just 1 for your quotient. So what that tells us is that we have a horizontal asymptote, so that's our type of NVA, but it happens to not be the x-axis. You have to have a 0 for it to be the x-axis itself. Okay, so the conclusions that we can make based on this form, well, first of all, if you're just given your function with some kind of a fraction, polynomial over polynomial, the numerator tells you about the zeros, the denominator tells you about the vertical asymptotes. And so what we just saw is when the degree of the numerator was less than the degree of the denominator, in that second example, you have the x-axis, the line y equals 0, as your horizontal asymptote. If the degree equals, like the third example, the degree of the numerator was exactly the same as the degree of the denominator, you're going to have a horizontal asymptote still, but a different asymptote than the x-axis, anything other than the x-axis. And then here's one we didn't see in particular, but if the degree of the numerator is bigger than the degree of the denominator, there are two scenarios. Either it's exactly 1 larger, or more than 1 larger. If it's exactly 1 larger, then your quotient is just going to have a linear term. So you're going to have a slanted asymptote, an oblique asymptote. If it's more than 1 larger than the denominator, then you'll have either a squared function or a cubic or maybe a 4th power. In any rate, it's going to be non-linear. We haven't seen that yet, but get ready because it's coming. Okay, so now if you turn the page, we are going to actually find some equations here. And so in our first one, we're looking at this description. We've got A0, and we've got information about vertical asymptotes. So right there, we're thinking, oh, 0 numerator, vertical asymptotes denominator, but then we've got this NVA business. So the NVA tells us, well, look at this form. However, this we can just use to verify. If you know about zeros and vertical asymptotes, that's where I would say let's use this form. This is what we'll be able to write. Okay, so we have exactly 1, 0 at x equals -1, so that's going to be your numerator. And so this is just saying here's the form. So x plus 1 for the numerator, and then 2 vertical asymptotes, and then here we go. X is -4, and the other at x is 1, so x minus 1. So then what we're doing with this whole, the NVA is y equals 0, is let's test it out. Here, the degree of the numerator is x. The degree of the denominator is x squared. So the degree of the numerator is less than the degree of the denominator. Okay, what we just concluded is if the degree of the numerator is less than the denominator, then the x-axis is your horizontal asymptote. That's line y equals 0. And what do you know? That's what we wanted. So we can do a smiley face. Okay, so in our next example, we have information about a slant asymptote, a vertical asymptote, or vertical asymptotes plural, and where we cross the slant asymptote. Well, remember the slant asymptote, the oblique asymptote, is one of our NVAs. So what we're looking at here is we are looking at this scenario in order to write our equation. Okay, and so we'll start off and just make sure on a test or a quiz you're not losing points for if it says write an equation. Make sure you're actually writing an equation. Okay, so start off with f of x equals, or y equals, but make sure that there's something on both sides of your equal sign. Okay, so we've got our function f of x equals, and we should have done that on the first one. Of course we did. Okay, and so we've got this NVA, slant asymptote, at x equals 2. We don't need the y equals anymore because that's the f of x equals. Okay, this is the form of our function. So there's our x plus 2, our NVA, right here. And then the intersection up here is really the x value of the intersection point. So let's look over here. It crosses the slant asymptote at x equals 1. And we're always doing opposite, so we're going to say x minus 1. And then the denominator is going to be our vertical asymptote. So here are our two vertical asymptotes. So I'll go ahead and write those. You can check yours. And then if we wanted to double check and make sure that this made sense based on our conclusions over here, since we have an oblique asymptote, we've got a slant asymptote, our degree of our numerator should be exactly 1 greater than the denominator. So be careful here because this is not in the right form, right? We need it in this form to be able to tell that. So remember, if you were going to combine these fractions together, it's sort of like if you have a mixed fraction, you take your denominator, multiply it times what you're adding by, and then add it to the numerator. So I'm taking my x squared, that's the total degree in the denominator here, x times x, then I'm going to multiply that by x again. So that's x cubed adding to x, so the degree of the numerator is really x cubed. And the degree of the denominator, like we just said, is x squared. So the degree of the numerator is exactly 1 more than the degree of the denominator, which is exactly what we were hoping for because we have information about a slant or oblique asymptote. Okay, so now we are going to skip ahead. So I'll go to the next page, and you'll come back to the other examples later. So we can also write our equations for graphs, not just descriptions. So if you look at this graph, there's a whole bunch of information that we can just write down right away. We're going to fill in all the blanks. And so the one thing you need to keep in mind is if your points look like they're on grid intersections, like these two, then they are on grid intersections. Okay? This is not a perfect science, so not everything really is in the exact spot. So for fractional values, if it looks like it's a fractional value in between two grid intersections, then it is. But you cannot assume that it's exactly 1/2. We're going to have to calculate that. So this one is between grid intersections, our Y-intercept, and so is our intersection with the NVA. It's somewhere between 3 and 4. We don't know exactly where. This is somewhere between 0 and 1. We don't know exactly where. What we do know, though, is we have no holes. You see no holes on the picture, so we can include that. We also know that we have 2 zeros, right? And those do appear on grid intersections. So we have a 0 at 2 and 3, so we'll write those as ordered pairs. We know at least for the y-intercept that the x value will be 0. And we can see 2 vertical asymptotes, one at 4, one at 5. We'll write those equations. And we can see our non-vertical asymptote here at y equals 1. And so with that, we know that the intersection with the NVA will have a y value of 1. We just don't happen to know the x value yet. Okay, and then we can also tell all the way to the left we are approaching our NVA from below all the way to the right from above. And our NVA, remember, is 1. Now, my little recording sheet here is a little bit off, and I don't remember if yours is, but if yours says positive infinity and then negative, let's just switch it to negative then positive. I think I have switched all of the tests and quizzes by now, but let's be consistent with what we've been doing. Okay, so I'm going to switch those. So as x is going towards negative infinity, that's over here. Remember, like I said, we are below. And as x is going towards positive infinity all the way to the right, we're above that non-vertical asymptote. Okay, so then last, before we write our function, let's look at the sign chart from the graph. So remember, in your sign chart, you're using your 0s, 2, 3, and your vertical asymptotes, 4, 5. So everything up until 2, right here, everything to the left is all above the x-axis. Okay, so that means everything over there is positive. On your sign chart, up until you get to 2, you should show positive. Then in between 2 and 3, nice thing, we went in order 2, 3, 4, 5. So in between 2 and 3 on the sign chart, our function dips below the x-axis. So in between 2 and 3 here, it should be negative. Then from 3 until 4, your vertical asymptote, it crosses over the x-axis, it's all positive. And then between 4 and 5, everything's negative. But then after 5, all of these x values over here are all positive. So after 5, your sign chart, after 5, your sign chart should be all positive. Okay, so then let's go ahead and try to write our function. Okay, remember, if you know about your 0s and your vertical asymptotes, the easiest way to write your function is going to be in this form, when we know about 0s and vertical asymptotes. So that's what we'll do. Okay, the 0s will be in the numerator, x minus 2 and x minus 3. The vertical asymptotes will be in the denominator, x minus 4, x minus 5. So we're pretty sure this is our function, but we will need to verify it. So for starters, we can verify by finding our y-intercept. Find the y-intercept from the function, plugging in 0 for x everywhere. What we're looking for is a positive value between 0 and 1. If that doesn't work, chances are we have to fix our function. So in this case, when we plug in 0, we should get 3/10. Well, 3/10 lies between 0 and 1, so that's looking pretty good. Okay, so then to figure out the intersection with the function and the NVA and further verify if that looks correct, if it's somewhere between 3 and 4, then we can safely say that this is our function. Okay, so first let's expand this out. Expand out the numerator, x squared minus 5x plus 6. And expand out the denominator. All right, x squared minus 9x plus 20. All right. So from there, we'll do our long division. And so x squared goes into x squared once. Hey, so far so good. That's kind of what we were looking for since our NVA here is 1. And we'll subtract off. What we're looking for here is the intersection. So we're looking at the remainder. Set that equal to 0. And then go ahead and solve. Okay, and I'm okay if you write it as a top-heavy fraction, 7/2. But what we're looking for is that between 3 and 4? And so what we're really thinking about, instead of the top-heavy fraction, we're really thinking about that mixed fraction value, 3.5. All right, well, 3.5 is certainly between 3 and 4, so that looks correct. So we can safely assume that our function that we wrote up here, f of x equals quantity x minus 2, x minus 3 over quantity x minus 4 and x minus 5 is the correct function.